All right, part 2 of section 3.5. Just finished going through some angular velocities and getting those in the right unit. Number 2, there's just a whole bunch of short problems here. We know the formula V equals R omega. So 3 letters, 3 variables. If you know 2, you can figure out the third. And so there's just a whole bunch of short sentences that describe 2 of the 3, and we're going to find the third one. And of course, you can see them all on the filled-in examples. I'm going to do some of them and let you guys look through the others. All right, so a point goes 8 meters per second. So sometimes the deal here is figuring out which ones do I know. Now, and so a lot of the times that can be based on the units even. 8 meters per second, a distance per time, that's V right there. All right, so V is 8 meters per second. This is clearly a radius. So R equals 25 centimeters. Now, we saw this in a previous example. If you're going to use these formulas, there's V and R both have distances involved, and they would have to be in the same distance unit. So we can either turn the centimeters into meters or the other way around. This would be the same as 0.25 meters because there's 100 centimeters in a meter. So we know V and R, so we would like omega. Omega, divide both sides by R, is V divided by R, so it's just a matter of V, 8, over R, 0.25, and we get 32 if you punch that out. Now what's the unit? All right, so this was meters per second, this was in meters. The meters cancel. Omega is an angular velocity, so this should be in some angle measurement per time unit. Our time unit is seconds. But again, when you use these formulas, look here, we're using this version, and omega comes out. Well, if you put a number in for omega, it needs to be in radians per something. If omega comes out, it's in radians per time unit. So this would be 32 radians per second. And if somebody wanted it in degrees per minute, you could convert those units, but that's the answer that comes straight out of the formula. Okay, let's do letter B. A satellite traveling that fast, miles per hour, that's a linear velocity, distance per time, right? So 7,400, and I'll actually write miles per hour. 1 orbit in 13 hours, all right? Well, that tells you how fast it's rotating. It's making 1 full rotation or 1 revolution or 1 orbit in 13 hours. So that would be omega, and we're getting 1, we'll even write orbit or rotation, 13 hours. Okay. So V equals R omega, you can also use to find R. If you divide both sides by omega, R would be V divided by omega. So now the only thing is, if you're going to put a number in for omega, it has to be in radians. So we got to multiply by 2 pi radians in 1 orbit. So we have 2 pi over 13, and now it's in radians per hour. Okay, so then the radius is 7,400 divided by 2 pi over 13. All right, so you'd have to punch that out, get out your calculator. If you do it to the nearest whole number, I got this. And so then what's the unit? All right, well, the 2 per hours, miles per hour, radians per hour, the hours cancel out. We have miles and we have radians. And now again, radians is this ratio or a scalar that turns a arc length into a radius. But another way to look at this is just that it's a radius. It's just a distance. What's our distance unit? And that would be miles. So apparently, in terms of distance from the center of the Earth, this satellite would be that far from it. All right, so that one we had V and omega. You found R. Why don't you try? We got C, D, E, and F here yet. See what you can get out of those guys. I'm going to do one more, but if you want to pause and try the rest of them, that would be a good idea too. So this is after the pause now. How about letter D? I won't give you problems that have sneaky things in them like I'm trying to fool you, but this is how something would be stated in real life too. 12-inch saw blade. Okay, well, what does that tell you? And that's just a distance across the saw blade, but it's across the whole entire thing. This means we have a radius of 6 inches. RPM, revolutions per minute. Right? This is not a linear velocity, not miles per hour, meters per second. Revolutions, so we're talking about how fast something's rotating. So that's omega, 1200 revolutions per minute. And of course, if we're going to use V equals R omega, we need that in radians. So we multiply by 2 pi radians. And the 2 pi goes on top because we want to cancel the revolutions. So one on top and one on bottom. That'll happen nicely. And this would be 24,000 pi. And now we're in radians per minute. And so our velocity then, well, it's R times omega. So 6 times 24,000 pi. So in other words, a big number. I got an extra 0. I definitely got an extra 0 in there. 2,400. Never mind that guy. If we punch that out, 45239 is 6 times 2,400 times pi. And our units, okay, it's a velocity, so distance per time, like miles per hour. But in this case, our distance is inches, and our time unit is minutes. And the only thing that's not very attractive about that is that we can't visualize that at all. That's a whole ton of inches, and it's happening in 1 minute. So how fast is that? Well, you could convert things to miles per hour, inches per second, maybe. That would help a little bit. It's pretty darn fast, no matter what it is. But that's a hard unit to understand and have a good idea on. All right, E and F, I will let you look at those on the filled-in document. Give them a try first, possibly. The last 2 pages are the group exercise pages. I think I'm gonna let you do number 2. I'm gonna just look at number 1 and get that set up. 12-inch disc. Well, that's actually like the 12-inch saw blade. Radius 6 inches. And actually, this is very similar. 33 1/3 RPMs. And that was a classic angular speed for a turntable, 33 1/3. All right. Now, again, it's RPM, just like that saw blade. So this is an angular velocity, and linear velocity is V, which we're going to try and find. So omega is 33 1/3, which for our computational purposes is actually better as a improper fraction. So how many thirds is that? Well, 33 wholes is 99 thirds, plus we got one more, so we have 100 over 3, and this is revolutions per minute. And as I hope you're getting accustomed to, times 2 pi radians over 1 revolution. So the revolutions cancel, and we're left with radians. So we have 200 pi over 3. And this would be radians per minute. Now you could punch that out as a decimal if you want to. But we'll do all our computations in just a sec. All right, so V is R omega, and we've got omega in terms of radians. So 6 times 200 pi over 3. If we actually cancel, which we could do, we get 400 pi, which, if you punch it out, is 1256. And just like in our saw blade case, that's inches per minute. All right, inches from the radius per minute from our angular velocity. It doesn't say what unit to put the answer in, but maybe to help us grasp this a little bit, how many inches in a second then? All right, well, if we want to cancel minutes, which are on the bottom, we would have to put minutes on top and 60 seconds on the bottom. And if you do 1256 over 60, that's about 21. And now our unit would be inches per second. And I think you could better visualize something moving 21 inches in 1 second. Okay. Like I said, I'm going to let you guys do number 2. Yep, and I'm going to let you do number 3. Got a little unit change to do with that guy. You're going to find omega, which will come out in radians per minute, and you need to convert that to degrees. I'm going to do number 4. This is one of those personal experience kind of story problems. I have a brother that lives in Columbus, Ohio, and a brother that lives in Lexington, Kentucky, and to get to their houses, we take a similar route, and we actually take this path. We go down toward Fort Wayne and head east into Ohio, which is along US 30, and you go by hundreds and hundreds of huge wind turbines. They just seem to go on for forever. And I actually looked up online to see how big they were, and this is just what I observed while driving past hundreds of them, is that, yeah, when they're moving about 1 full rotation in 4 seconds. So, here's the question. Linear velocity of the tip of one of those blades in miles per hour. So here it goes. And again, these are all group exercises. These are perfect for you to just stop, pause, try them out, see what you get. All right. So each blade is, they look kind of like this. They got 3 blades, and each one is 148 feet. So that's our radius. 1 full rotation in 4 seconds is telling you how fast they're rotating. So that's omega, and we're going to use that to find p. So omega, 1 rotation in 4 seconds. All right, we need this in radians, so for what seems like the gazillionth time, 2 pi radians over 1 rotation. So if we cancel, that's pi over 2 radians per second. Actually, if you think back to that, pi over 2 is 90 degrees. 1 full rotation in 4 seconds, yeah, 90 degrees in 1 second. That's exactly what we're saying. So then V, R times omega, 148 times pi over 2. So we have 74 pi. And that would be measured in, well, this is a linear velocity, so distance over time. Feet from the radius per second from the angular velocity. But, all right, 74 pi, and you could punch that out to see what that is. Somewhere in the 200s feet per second in terms of how fast it's going. So how fast is that in miles per hour? All right, here it goes. We did this conversion one other time. There's 5280 feet in a mile, so does 5280 go top or bottom? Well, we want to cancel the feet, so 5280 goes on the bottom, since feet are on top. 1 mile on top. And also, we want hours, not seconds. Now, there are 3,600 seconds in an hour. So does that go top or bottom? Well, seconds on the bottom to cancel them, 3,600. Seconds on the top for 1 hour on the bottom, which is perfect because that'll give us miles per hour. And if you punch that out, you get 158.5 miles per hour, which is pretty fast. And it's no wonder that these big windmills, even though they don't look like they're moving too fast, can kill birds quite easily, especially with the tip of them going almost 160 miles per hour through the air. All right, number 5 is just looking at how changes in one of these three quantities makes for changes in the other. It's based on V equals R omega. So even I'll just do some brief comments, and you can see the actual work in the notes. If you double the radius, but something keeps rotating at the same speed, how does the linear velocity change? So that's like if you're riding a carousel and you double how far you are from the center, but the carousel keeps rotating at the same rate. What happens to your linear velocity? Well, if you double your radius, it's going to directly double the velocity, right? So the punchline here is doubling your radius doubles your velocity. So what if the velocity is doubled, but the radius stays the same? So the amount of distance you're covering is twice as big, but you're staying the same distance away from the center. All right, what's the new angular velocity? Well, if this quantity gets twice as big and this quantity stays the same, then this one's going to have to get twice as big as well. Hopefully that makes some sense. If you just start running, you're running in circles and you just start running twice as fast, yeah, how your rotational velocity, how fast you're going around your circles, is also going to get twice as fast. All right, how about you're riding on the carousel, your angular velocity doubles, so all of a sudden the carousel starts going twice as fast, rotating twice as fast. But you want the distance you're covering to stay the same. Well, do you move further away from the center? Do you move closer to the center? What do you do? Well, with V equals R omega, if this guy gets twice as big, but you want this to stay the same, when you're multiplying these two, if this one doubles, this one's got to cut in half in order for their product to stay the same. And you could see that with the actual numbers as well. If you take the recommended values here and actually put them in and do the computations, you can see that in the notes. Okay. Let me know if you have questions. Let me know if you want an in-depth explanation of any of these particular examples. I hope you paused and went through some, or before you go look at the filled-in notes, go try to do the ones that I didn't do and see if you can get those answers, but then go to the notes and check them. All right, that's going to be it for Chapter 3, in fact.